Okay, so let's look at another example using an equilibrium table. This one I'm going to call a perfect square, and we'll see why in a minute. So here's an example. It says hydrogen iodide decomposes to hydrogen gas and iodine gas. So it says at 800 Kelvin, the equilibrium constant which is the Kc, equals 0.016. If 0.50 moles of hydrogen iodide is placed in a 5.0 liter flask, what will be the composition of the equilibrium mixture in molarities? I'm just going to say molar composition. Of the mixture. Okay, so there's a lot of different ways that these questions can be presented. There's a lot of different pieces of information that could be given or left out, and then you're determining what you're solving for and what steps you're going to take to solve it. So that is a really important part of solving these problems, is being able to distinguish what steps am I going to take to get to the answer. So let's just see what information we're given here. So first of all, the first thing that you're always going to do is you're going to write the chemical reaction. I'm going to say write the balanced reaction. And then you're going to assess what information that you have. So let's do that first. Hydrogen iodide decomposes, which just means breaks apart, to hydrogen gas and iodine gas. Again, hydrogen iodide is a gas. Hydrogen and iodine are both diatomic. This is not balanced. I have 2 hydrogens, 2 iodines, so I'm going to put 2 here. Remember how important it is to have these coefficients correct, because the coefficients are going to come into place 2 in 2 places. 1 with the change between initial and equilibrium, and 2 because whatever the coefficient is going to be the exponent in the equilibrium expression. So we wrote the balanced chemical reaction. Next, let's see what information is being given and what information is being asked. It gives us the Kc. Kc is 0.016. So I'm going to write that here. Kc equals 0.016. Remember what the Kc is. The Kc is the concentration of the products over the concentration of the reactants, both of these at equilibrium. So let's write our equilibrium table and see how we can solve for these concentrations when we're given the actual value of the Kc. So I'm just going to do R, here's my reaction, I is initial, C is change, E is equilibrium. This row right here that we are going to fill in, the equilibrium row, that's what we're going to use for the Kc. So we need to figure out how are we going to solve for this equilibrium row. So it tells me that initially we have 0.50 moles of hydrogen iodide placed in a 5-liter flask. So we need to solve for the molarity of hydrogen iodide. So moles per liter, 0.50 moles in 5.0 liters means that I have a molarity of 0.10 molar. That's the concentration of hydrogen iodide. That's what goes right here. The initial concentration of hydrogen iodide, the amount that we start with, is 0.10 molar. We're not starting with any reactants. When you start a chemical reaction, you're not starting with any initial amount. Unless it's a weird situation where they tell you what the initial concentration of the products are, you can always assume that the initial concentration of the products are 0. So now let's see what's going on with the change. So remember that the reactants are always decreasing. The products are always increasing. It's increasing or decreasing by a factor determined by the stoichiometry. So this is going to be minus 2x because this has a coefficient of 2. This is going to be plus 1x. This is going to be plus 1x because both of these have coefficients of 1. Now I'm going to bring everything down to here. So I'm going to say what goes down here is 0.10 minus 2x. That's this part. This is 0 plus x is x. 0 plus x is x. So now I'm going to plug this into my Kc. So remember the Kc is the concentration of the products over the concentration of the reactants at equilibrium. I'm just going to write it out again specific to this equation. So I'm going to say the Kc is the concentration of the hydrogen gas at equilibrium times the concentration of the iodine gas at equilibrium over the concentration of hydrogen iodide squared. Because, again, this coefficient here comes into play 2 places. Not only does it affect the change, it also is the coefficient, the exponent in your Kc. So now what I'm going to do is I'm going to plug each of these in to here. So I'm just going to write this again. I'm going to write Kc equals, what is the concentration of hydrogen iodide at equilibrium? It's x. Times the concentration, I think I said hydrogen iodide, I meant hydrogen gas. The concentration of hydrogen gas times the concentration of iodine gas, which is also x at equilibrium, over the concentration of hydrogen iodide squared. And all of this equals the Kc, which we were already told in the problem, is 0.016. Okay, so now we have this. We have x and x on the top, 0.10 minus 2x squared on the bottom, and then 0.016 on the top. I'm going to rearrange this. I'm just going to put this from left to right. 0.016, I'm going to take these two x's and I'm going to multiply them together. So I'm going to say x squared on the top, and then on the bottom is 0.10 minus 2x squared. So the reason that I call this example a perfect square is because now this is what we have here. This is an example of something called a perfect square, meaning I can just take the square root on both sides to solve for x. If you do not have a perfect square, meaning that not both the top and the bottom is squared like this, you can't just take the square root, you would have to use the quadratic formula to solve for x. We'll do an example of that later. This is an example where you do not have to use the quadratic formula. Because the top and the bottom are both squared, I can just take the square root of both sides. So when I take the square root of both sides, I'm going to get something like, if I take the square root of 0.016, I get, let's say, 0.126 equals, now I've gotten rid of these squares, x over 0.10 minus 2x. So now I'm going to multiply both sides by 0.10 minus 2x to get rid of this denominator. So when I do that, 0.10 times 0.126 is 0.0126 minus 2x times 0.126 is 0.252x equals x. So I got rid of that denominator. So now I'm going to move this to the other side, plus 0.252x plus 0.252x. I'm just going to bring this all down here. I'll say 0.0126 equals 1.252x, because remember this x is 1x. So now I'm going to divide both sides by 1.252, and I'm going to get that x equals 0.01006. That's what x is. Well, let's see how many significant figures my answer should have. It should have 2. So I'm going to say x equals, here would be my 2 significant figures, x equals 0.010. This is also where a lot of people make a lot of mistakes, is these are kind of long and complicated problems, and oftentimes people get to the end right here and they solve for x, and they say, great, I'm done, I solved for x. But the question isn't asking for x, the question is asking what is the molar composition of the mixtures, which means what is the concentration of all of these things. So it's saying, what is the concentration of hydrogen iodide? What is the concentration of hydrogen gas? And what is the concentration of iodine gas? That's what the question is asking when it says, what is the molar composition? I'm going to use x to solve for that. So x is 0.010. So if the molar composition is 0.10 minus 2x, which is 0.010, 2 times 0.010 is 0.020. 0.1 minus 0.020 is going to be 0.080 molar. This is the concentration of hydrogen iodide at equilibrium. For hydrogen, it's just x, so that means it's 0.010 molar. For iodine, it's just x, 0.010 molar. So this is the question that we're being asked to answer. What is the molar composition of everything, of the mixture? And you need to use this equilibrium table to solve for x. Here we had a situation where it was a perfect square, so we could solve for x without using the quadratic formula. Once we solve for x, we're going to plug x back in to get the molar composition at equilibrium.